Hey, this video contains the notes for section 10.6 about alternating series. An alternating series is a series that alternates signs, positive, negative, or negative, positive. What do we know about alternating series? Well, the first thing is that if the absolute value of the terms in series, an alternating series, approaches 0, then the series converges. Now, that's a pretty bold statement if you're thinking about all the other things that we've said so far and all the tests that we have to do, the ratio test, and so on. This is a pretty easy and pretty strong statement, or pretty easy to determine, pretty strong sweeping statement. This says that as long as the absolute value of the terms is decreasing to 0, then it doesn't matter. You can throw all your tests out the window. The series converges. So, for example, here's an alternating series. In fact, you could call it's the alternating harmonic series, right? But this is very different than the harmonic series because we're subtracting, we're alternating, adding, and subtracting. And if you think about what's happening here, well, according to this, it converges, right? Because the terms are getting closer and closer to 0. So the fact that the non-alternating harmonic series is divergent didn't matter here. So long as it alternates and the terms get smaller, it's going to converge. Let's think about why that is true, why this statement's true. If we start out, think about like on a number line, here's 0 and here's 1. So our series starts off with 1, right? When we just take one term, it's 1. And then we're subtracting 1/2. That brings me to here. Then I'm adding 1/3, which would bring me to about here or so. Right, and then I'm subtracting 1/4, and the amount that I'm adding and subtracting keeps getting smaller, so I'm bouncing back and forth, always getting closer and closer to something. And that something is what the series is converging to. In this case, do you want to know what this one converges to? Can you handle it? Converges to the natural log of 2. Can you believe that? It's kind of crazy. But it does, and we'll prove all that stuff more later in this chapter. But that actually does converge to the natural log of 2. Now, a little bit of vocabulary. It's not going to be a huge, big deal for us, but I am going to include it in your notes here. There is vocabulary to describe the different types of convergence here. We say that this is all for alternating series. If the absolute value of the series converges, we say, sorry, let me put the summation sign here. If the sum of the absolute values converges, we say that the series converges absolutely. And here, absolutely, it's not as in like, yeah, really, man. It's like absolutely like absolute values, right? It converges absolutely. Its absolute values converge. And if not, we say it converges conditionally. So let's take our example here. Does this converge absolutely or conditionally? Why don't you pause and think about that for a minute. Well, the absolute value of that, if we take our example here, the absolute value of those terms would be positive versions only. And does that converge or diverge? This diverges. It's the harmonic series. So, did the absolute values converge? No. That means it converges conditionally. So this series right here converges conditionally. And if you're trying to figure out or make sense of what this conditionally means, it's on the condition of the alternating signs, right? It converges conditionally. The condition is the alternating signs. It would not have converged if it didn't have alternating signs. If it did, then we'd say it would converge absolutely. It didn't even matter that the signs were alternating or not. It was going to converge no matter what. All right. Then the only other thing that remains for us to talk about, although it is an important thing, is the error involved in an approximation using an alternating series. Much for the reason we looked at in our little picture here, bouncing back and forth. You can never be off. If you approximate something, like this one, I'm claiming that this series here approaches the natural log of 2, right? Well, you can never be off in an alternating series by more than the next term. So, for example, I'll explain this by example. I think it's the best way to do it. I'm claiming that the natural log of 2 is equal to the infinite series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus etc. Now, who has time, really, to spend the rest of eternity adding and subtracting these little fractions to figure out exactly what this is? We're probably just going to want to find some kind of approximation. Well, in an alternating series, I know that if I want to approximate natural log 2, I could just take some of these terms, right? Take 1 minus 1/2 plus 1/3 minus 1/4, and I could stop there, right? I could just stop there. Well, this particular approximation, we could call that's the partial sum of the first 4. It's like S4. I know that error, the absolute error, in other words, the difference between this approximation and the target, the difference between those, I'm just putting absolute values because I want the positive version of the difference, that's all. That's going to be less than the next term, the very first term we didn't include, the positive version of that. Well, that's interesting. So let's actually do that and see what happens here. If we put those all in terms of, what would the common denominator here be? 12. This is 12 twelfths minus 6 twelfths plus 4 twelfths minus 3 twelfths. So that's what, 7 twelfths? I think, right? 12 minus 6 plus, yep, 7 twelfths. And according to this idea, this number right here, 7 twelfths, should be within 1/5 of the natural log of 2. And I'll leave that for you to check in your calculator. That's 0.2, right? So we should be within 0.2. That's pretty sloppy error, though, 0.2. That's not even 1 decimal place of accuracy. So what if we wanted, for example, to approximate what's the natural log of 2 using this series to 2 decimal places of accuracy? Well, we've got to talk first of all what it means to be within 2 decimal places. have 2 decimal places of accuracy. That actually means we want the error to be less than 0.0. You might think it'd be 0.01, but we need to, that could get us off by an entire decimal place there. So we go half of the 0.01. If you want to be accurate to this decimal place, you put zeros up to that decimal place you want accuracy, and then a 5. And that'll get us within the decimal place that we want, right? So it wouldn't round to a different decimal in that place. So let's see. What is this as a fraction? That's 5 thousandths, or 1 over 200. So that means to do this, we would have to use, I mean, since it's pretty easy to see how far we would have to go to get to a term that was smaller than this, would have to go 199 terms, right? Because the 200th term would be 1 over 200, and that's what we need. We want our error to be less than or equal to that. So that's pretty far out. What does that tell us about this series? It tells us that this series, although it does converge on the natural log of 2, it converges very slowly to that value. I'll show you another interesting one. We do another example of this type. I'll make another claim that we'll prove later. I think I might have alluded to this before. But here's a series. 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial, etc. Guess what that's equal to? You should try a few terms in your calculator and pause and see what it's coming close to. But sure enough, it's E. Later in this chapter, we will prove that this is true. But we're not there yet. Now this, on the other hand, this series actually converges very quickly to E, because these numbers are getting very big, right? We're adding very smaller and smaller fractions. So let's try to use this series to approximate E to, let's see, how about 3 decimal places? 3 decimal places. So that means we need to find the term, you know what? We can't use this one. What's wrong? What's wrong? What's wrong with this? You know what's wrong. What's wrong? The problem is, this is not an alternating series. But we can fix it. If we make it alternating, like this, whoops, that's still plus. Then you're not going to believe this. That converges to 1 over E. Crazy. And the 1 minus 1 here, by the way, those just cancel out, right? So this series here, we'll use this one. That converges to 1 over E. And as I said before, it's going to converge very quickly. So in this alternating series, we just need to go out far enough to find a term that is less than, we want our error to be less than 3 decimal places. I'm going to put a 5. And let's see, I need to find the first term that's less than that. So we can just kind of guess and check that. I'm just going to run and grab my calculator. So we can try some terms and see, just try to find one that's less than this. 1 over 5 factorial, I don't think that's going to do it. So we could try 1 over, excuse me, 6. If you go in the math menu over to probability, number 4, that's your factorial sign. 0.0014, that's getting close, but that's not less than this. So we'll try 1 over 7 factorial. That's to the negative 4, that would be let's just write this down. 1 over 7 factorial is equal to 1.98 times 10 to the negative 4th. That would be 0.0001998, etc. And that's less than this, right? So that's how far we need to go up to which term do we have to include now? Think about that for a second. How far do we have to go in our approximation? Do we need to include that term? The answer is no. This is the next term. We need to go up to but not including this term, and that will get us our error. If you think about, like, what's the logic here? Well, if I went up to that term, I would be adding something so small that it's not going to make the kind of difference that we're interested in anymore. So we just have to go right up to plus 6 factorial, and that should get me my desired accuracy. So let's check it and see if we did it. So 1 over, let me clear that out, 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial. I know the first few, so that's faster than getting the little exclamation point from the probability menu. 1 over 5 factorial plus 1 over 6 factorial. Let me make sure I got the signs right. Positive, negative, positive, negative, positive. And that, it gives me 0.368. That's 3 decimal places, right? And now we'll compare that to e to the negative 1, or 1 over e, and see if we got the right accuracy. 1 divided by e is, rounded to 3 decimal places, would be 0.368. And notice how far off those are. It's about 0.0002 off from each other, which was what we were looking at here. So that's pretty cool. That works for alternating series. Don't make the mistake, like I almost did, of using that piece of information with a non-alternating series. There's a way of doing this with non-alternating series that we'll talk about later in the chapter. It's not as nice as that. Alternating series error is great. It's just the error is less than the first term that you didn't use. So in this case, we went 1 over 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. The error, how far off we are from the real actual sum that we're converging to, is not bigger than the next term. And there will be a few homework problems for you to try using that. And I think that's all. Actually, one more quick thing. Can you use the ratio test for these? Sure. To see if an alternating series converges, you can check for absolute convergence using the ratio test, but just use the absolute value. So if the limit as n approaches infinity of this is less than 1, then what would we say about the series? It converges, right? If the limit's less than 1. Which kind of convergence? Absolute, right? Absolute value signs. Converges absolutely. In other words, we just did it like we would have done with any other series. We're ignoring the sign of flip-flopper. So when you do this, if there's like a negative 1 to the whatever, you just throw it out, right? You just use the terms and see if it converges absolutely. Of course, if the limit as n approaches infinity of the terms is 0, then it still converges, right? If it's alternating, the terms going to 0 is a strong enough condition for convergence. It might converge conditionally, but that's enough for it to converge. What about if the terms are not approaching 0? Well, we know if something has any chance, is going to have any chance of converging to anything, the terms need to be going to 0, whether it's alternating or not. So if the terms are approaching something else, then that's game over. And that's video over.